Okay, so now let's take a look at a circuit that is containing an ideal op-amp where we want to find some other value. So for this particular circuit, we're looking to find something called our closed loop gain. And so this is different from our open loop gain that we've talked about previously. Our closed loop gain we're going to identify by the variable a sub c, so c for closed loop, and that's going to be defined as our output voltage divided by our input voltage. So of course we have our output over here on the right, and for this particular circuit, our input for the circuit is this Vs over here on the left side. So in order to analyze this circuit, we're going to use the properties of our ideal op-amp that we discussed in a previous video. So the first thing that we can look at is that we know that our differential input voltage, V sub D, which was defined between our two terminals, like such, we know that that input voltage is 0. So we can look at our non-inverting terminal, which is our positive terminal, and we can see that that is connected directly to ground. So we can come back down here and we can say, well, we know that V sub plus is equal to 0. So that's just a way of me saying that our non-inverting terminal is equal to 0. We want to be careful not to confuse that with our V plus, which is our power supply. So we found that our non-inverting terminal is at ground, and if the difference between the two terminals has to be 0, then of course what that means is our inverting terminal is also at 0. So we can say that this terminal up here is also at 0 potential, or we could just come over here and we could say this point right here has 0 potential, V equals 0. One thing that you might see as you're working with electronics, if we're talking about this inverting node, this negative input of our op-amp, we would say in this case it's at a virtual ground. And so what the virtual ground means is that it's essentially at a ground potential, but there's no physical path to ground. Okay, so just sort of a little idea as we're looking at other circuits later on in other classes. So our second main property of our op-amp was that we had 0 currents into an ideal op-amp. So 0 currents into our ideal op-amp. And so if we come up here to our circuit, that means that if we define some currents here and here, that they're both going to be 0. And remember, that's because we said an ideal op-amp has an infinite input resistance. Okay, so in order to make our analysis a little easier, what we can do is define some other currents. So we can define a current through this 10 k ohm resistor, and I'm going to call this IS because it's right next to that source Vs. And I can also define a current up here going through this 20 k ohm resistor. Like we're going to see with some other examples, you can define these currents going in whatever direction you like, so long as you keep in mind your passive sign convention. And I'll talk about why I've defined that top current as IF a little later on. So if we know that we have 0 current into our inverting terminal, then we can do a KCL at this node here, and we can see, so from KCL, we see that our IF is equal to negative IS. So essentially both of these currents, IS and IF, come into the node and nothing else comes out other than, of course, that 0. So now let's define further what our IS and our IF are. Well, to make it a little easier to see, I can explicitly define these voltages. Of course, it's implied that this Vs is relative to ground. Well, since this point here is at 0 potential, then we could write explicitly with polarities our Vs like such. Same thing with our output voltage. Because this output voltage is implicitly related to ground, we can write that it's positive here and negative over here, which is ground, or a virtual ground at the very least. So we have V naught across there. Okay, so if we want to write these IS and IF in terms of our voltages, we can say our IS is going to be equal to Vs over our 10 k ohms, and we also have that our IF is going to be V naught over 20 k ohms. And so notice that because both of these reference currents were going through reference voltage drops, we just used a positive sign when we used this Ohm's law here. Okay, so now we're going to combine sort of these three equations, our IF equals negative IS, as well as these two equations here. And we're going to see we're left with something with VS, V naught, and numbers. So then we can rearrange it to get our closed loop gain, which is what we were initially asked to solve for up here. So let's go ahead and do that. So substituting in for those two equations, we have our IF, which is V naught over 20K, is equal to negative IS. Well, our IS was VS over 10K. So we can then solve, rearrange that a little bit. We get our A sub C, which is equal to V naught over Vs. And we find that that is equal to negative 20K ohms divided by 10K ohms. And so, of course, our K ohms are going to be canceling out, so we're just going to get a dimensionless value of negative 2. So that would be our answer for this problem, a closed loop gain of negative 2. Something we're going to touch on a little more later, we noticed that because this Vs was connected to our inverting input, our gain is then going to be inverting that input such that our output is basically 180 degrees out of phase. So a couple notes before we finish this example. If we were looking instead with our non-ideal model, let's see what we would get for our closed loop gain in that case. And so this calculation is done more fully in the textbook, but I just want to throw out the numbers here and the results so we can compare. So with our non-ideal model in the textbook, we have been told our op-amp has some open loop gain of 2 times 10 to the 5th. And so remember, ideally our open loop gain is infinite, but here it's a little smaller than infinity. We're told that our input resistance for our real op-amp is 2 mega ohms. So that's 2 times 10 to the 6 ohms. So ideally that's infinite, but in this case, not quite infinite, but still pretty large. And then finally, we're told for our real op-amp in the textbook, we have an output resistance R naught of 50 ohms. Ideally, we said our output resistance is 0, but we can see 50 ohms is pretty small. So if we plug all of these things into that non-ideal model that we showed in a previous video, we end up getting a closed loop gain of negative 1.9999, so 4 nines and a 7. So now what we can do is, of course, we compare these two values here, and we see that negative 2 is very close to this negative 1.999997. So what we say is that using our ideal op-amp is a good approximation, and if we looked at all the calculations that are involved in going from these three inputs or these three variables to our closed loop gain, it's a lot more complicated than what we had to do up here for our ideal case. So that's sort of the advantage of doing this ideal case, at least as a first pass. One other thing I wanted to talk about relates to why I labeled this as IF. So let me go ahead and switch to a different color here. So why did I label this as IF? Well, when we introduce this 20K ohm resistor, we actually are introducing a feedback path. And so in this case, it's going to be negative feedback because it connects to our inverting terminal. So because it's feedback, that's why I've labeled that as I sub F, so we can call it our feedback current. And what we're going to see is that in general, and sorry, let me take a step back. We're calling it feedback because we're taking a portion of our output and we're feeding that back into our input of our op-amp over here. Because we're going into this negative terminal indirectly, we're saying it's negative feedback. So typically when we have negative feedback, our gain is going to get a lot smaller because remember, if we didn't have these resistors, ideally our gain is infinite. But now we see that our closed loop gain is negative 2. But the advantage of doing that is that our stability, in most cases, is going to be greatly increased. And so we're going to touch on that more in a couple classes later on, but I just wanted to make sure you're aware of that. Okay, so that's all for our first example with our ideal op-amps.